Welcome, everyone. Today, we're going to talk about a major leap forward in artificial intelligence, RLAnything, the fully dynamic reinforcement learning system. If you look at the diagram here, you'll see our core philosophy. Instead of treating the environment, the policy, and the reward model as separate, isolated pieces, RLAnything forges them together into a single, closed-loop ecosystem designed specifically for agentic AI. To understand why we need this, let's look at the current bottleneck in agentic reinforcement learning. Right now, when agents tackle real-world applications, like navigating a computer's graphical interface or writing long-horizon code, they face what we call the sparsity void. They start a task, take dozens of steps, and only get a binary pass or fail at the very end. The flaw here is obvious: binary outcome rewards are just too sparse. They fail to give complex agents the step-by-step course correction they desperately need. As a result, exploration gets completely stifled, and the agent's learning curve just flatlines. This brings us to the RL paradigm shift. Traditional RL relies on rigid setups, environments are static and fixed to predefined datasets, reward models are bottlenecked by human-written scripts, and policy signals rely on those sparse, final outcomes. RLAnything completely flips this script. Our environments dynamically adapt to match the agent's capability. Our reward models are self-optimizing via consistency feedback. And our policy signals use integrated feedback, combining nuanced, step-by-step guidance with the final outcome. Think of RLAnything as a dynamic engine. It's a continuous loop. The policy outputs trajectories to the reward model. The reward model is optimized via consistency and outputs stepwise evaluations to the environment. Then, the environment adapts using critic feedback, generating appropriately scaled tasks to feed back to the policy. It's a fully dynamic ecosystem where each component continuously amplifies the learning signals of the others. Let's break down the three pillars of this system, starting with Pillar 1, Integrated Policy Feedback. We are moving beyond binary. Instead of waiting until the very end of a task to know if it failed, the policy receives nuanced, step-by-step guidance along the trajectory. But crucially, this stepwise guidance is strictly anchored by the verifiable final outcome. The impact? It drastically accelerates learning in complex, long-horizon tasks. Pillar 2 is our self-optimizing reward model. Usually, reward models are frozen after initial training. Not here. In RLAnything, the reward model uses the policy's ongoing trajectories as its own active training ground. Through joint optimization, it constantly balances step-level labels with overall trajectory quality. The result is an ever-sharpening evaluation signal that literally gets smarter right alongside the agent. Pillar 3 is automatic task adaptation. Static environments often cause agents to get stuck on impossible tasks or overfit to easy ones. RLAnything solves this by using an adaptation funnel. If the policy is performing too well, say, above 80% accuracy, we trigger a language model to make the prompt harder. If it's failing terribly, below 20%, we make it easier. By leveraging summarized error patterns from the reward model, the agent is perpetually kept in the optimal zone of learning. Let's look at this adaptation in action. On the left, a GUI agent is completely failing at a spreadsheet task with zero accuracy. We adapt the task by adding a hint to use the function wizard, breaking the stall. In the middle, a text game agent is finding the target cloth too easily. We adapt it by swapping cloth for a much rarer item, soap bottle, forcing deeper exploration. And on the right, a coding agent with a 100% pass rate is challenged with a new negative constraint, beautifully restoring the challenge. So, why does this matter? The synthesis of this framework is that adapting the environment doesn't just help the policy learn. Our theoretical proofs show that it mathematically prevents heavily skewed trajectory distributions. You need this balanced data to accurately train the reward model. In short, everything is connected. Modulating the environment is absolutely essential for optimizing the reward. When we put this into practice, the results are incredible. Let's look at multimodal GUI agents on the OS World benchmark. RLAnything dynamically outperforms established open-source baselines across the board, whether it's Chrome, VS Code, or local OS navigation. We achieved a massive 9.1% absolute gain in accuracy. This is a breakthrough for real computer control environments. The success continues with text and LLM agents. On the AlphaWorld benchmark, we saw an 18.7% jump in accuracy. As you can see from the training curve, our dynamic engine drastically accelerates the learning pace. By jointly optimizing the environment and the reward models, we reach a significantly higher converged accuracy compared to the old, static methods. And for agentic coding, the story is the same. On the live bench evaluation, we see up to an 11.9% gain in accuracy. By training the unit tests, which act as the reward alongside environment adaptation, we create fundamentally stronger coding capabilities. Best of all, these gains persist robustly no matter what downstream agentic execution framework you use. During this research, we found a truly surprising insight. Automated reward models actually beat human-written evaluation scripts. Traditionally, RL relied heavily on humans to write evaluation scripts, which severely bottlenecks scaling. Counterintuitively, we found that training the policy using only the optimized stepwise signals from the RLAnything reward model outperforms relying on human scripts. This is huge. It unlocks massive, automated environment scalability without human bottlenecks. This brings us to the flywheel in motion. As training progresses across GUI agents, text agents, and coding LLMs, you can see the system continuously generating and accepting new, valid tasks. The environment scales linearly, enabling active learning from endless synthetic experience. And despite this massive influx of new tasks, the system perfectly maintains an optimal difficulty level for the agent. To conclude, the next frontier of AI reasoning isn't just about making static models bigger. It is about building dynamic ecosystems. By forging the policy, the reward model, and the environment into a continuous, closed optimization loop, RLAnything unlocks self-evolving agents capable of mastering the noise, the nuance, and the complexity of the real world. Thank you.